Example 2.21. Two charges minus q and plus q are located at points 0, 0 minus a and 0, 0 a respectively. Question A. What is the electrostatic potential at the points 0, 0 z and x, y, 0? B. Obtain the dependence of potential on the distance r of a point from the origin when r by a, that is very much greater than 1. C. How much work is done in moving a small test charge from the point 500 to minus 700 along the x-axis? Does the answer change if the path of the test charge between the same points is not along the x-axis? Now let's discuss one by one. See here, minus q, that is at 0, 0 minus a, and plus q, that is at 0, 0 a, means we can say this is the dipole which one is coinciding with z-axis. So minus q, that is at a on negative z-axis from the origin, and plus q, that is at distance a on positive z-axis. Now first we want to find the electrostatic potential at the point 0, 0 z. So here consider the point on the z-axis at a distance z from the origin. So to find the resultant potential, simply we can take the potential at that point due to plus q charge, then potential at that point due to minus q charge. Clear? Now see, potential at point z, that is kq upon, now the distance between that point and plus q, that is z minus a, and for negative charge the distance, that is z plus a, but charge is minus q, so potential, that is minus kq upon z plus a. Take kq common, so 1 upon z minus a minus 1 upon z plus a. Now by taking LCM, simplify this one. So kq z plus a minus z plus a, and in denominator z minus a into z plus a, directly we can write that is z square minus a square. Now z cancelled. So k q a plus a, that is 2a upon z square minus a square. So q into 2a, that is the dipole moment P. So we can write the potential at a point on the z-axis at a distance z, that is kp upon z square minus a square. Clear to all of you? Now the point xy0, that will be on xy plane, and here this xy0, that is perpendicular to z-axis, and when z is 0 means it is passing through the origin. It implies that each and every point on the xy plane, that will be at the same distance from minus q and plus q. So potential at each and every point, that will be 0. So we can say that is the equipotential surface. Clear to all of you? Now see, we derive the equation for the potential, that is kp upon z square minus a square. Suppose that distance z we denote by r, then we can write the equation of potential, that is Kp upon r square minus a square. But if we take r that is very much greater than a, it implies that r by a that is very much greater than 1. So in that condition, we can neglect a square. So we can write V that is equal to Kp upon r square, means in this case, we can write the potential proportional to 1 upon r square. Now third question, how much work is done in moving a small test charge from point 500 to -700 along the x-axis? Now see here, both the points are on x-axis, and x-axis that is perpendicular to the z-axis passing through the center. So potential at each point on the x-axis, that will be 0, and therefore the work done to move any test charge from one point to another point, that is q into delta v, but delta v the potential difference, that is 0, so work done that is 0. Then it is asked if the path is not along the x-axis, then any change will take place? No, because work done that does not depends on the path. It depends only on the initial and final positions. Clear to all of you?